Hello everyone. Welcome to another episode of Deep Dive Knowledge Talk. What inspired the development of the diffusion transformer model in the context of image generation using transformer-based diffusion models? How does the architecture of the diffusion transformer differ from traditional transformer models in this specific application?
The development of the diffusion transformer model was inspired by the success of transformers in natural language processing, NLP, tasks, and their migration to computer vision tasks, such as image generation. This model was introduced by William Peebles and Saining Shelby in their study, Scalable Diffusion Models with Transformers. In the context of image generation, the diffusion transformer model differs from traditional transformer models by integrating diffusion models with the transformer architecture. This integration allows for the training of latent diffusion models based on transformers, providing a scalable approach to generative models for images. By combining the strengths of diffusion models and transformers, the diffusion transformer model offers a new way to generate images with better control and guidance, especially through the use of textual prompts or class conditioning.
How does the diffusion transformer model utilize the forward and reverse processes of adding noise to images and removing noise to achieve image generation? Could you elaborate on the role of classifier-free guidance in ensuring that the model adheres to prompts during this process?
Classifier-free guidance plays a crucial role in making sure that the diffusion transformer model follows our instructions accurately when generating images. Imagine you are trying to teach a robot how to draw a picture based on what you describe to it. In this case, the textual description you provide acts as a guide or a prompt for the robot to understand what to draw. Now, sometimes the robot might misunderstand or ignore your guidance, leading to incorrect drawings. To prevent this, classifier-free guidance is like having an extra set of eyes to supervise the robot as it draws. This technique helps the model pay closer attention to the prompts, ensuring that the images generated align better with what we want to see. In the context of the diffusion transformer model, this guidance mechanism ensures that the model doesn't overlook the prompts provided, maintaining a strong connection between the input information, prompt, and the output image. It helps the model go through the forward process of adding noise to an image, and then the reverse process of removing that noise, resulting in accurate and meaningful image generation based on the instructions given.
How does the diffusion transformer model handle the compression and decompression of images in a latent space? Can you explain the significance of transforming latent tensors into token sequences, applying positional encodings, and using patchify to divide tensors into grids for processing within the transformer models in this context?
Sure. Let's break it down into simpler terms. Imagine you have a magical book that can transform pictures into stories and stories into pictures. In the world of the diffusion transformer model, when we want to work with images, we first need to convert the image information into a language that the transformer model can understand. To do this, we take the raw image data, which is like a secret code, and we break it down into smaller pieces, just like how a jigsaw puzzle is made of many small pieces. Then, we convert these small pieces into a sequence of tokens, which are like words in a story. These tokens help the transformer model understand the image information better. Next, we use something called positional encodings, which are like a map that tells the model where each token belongs in the sequence. It's just like in a treasure hunt. The map guides you to the right spot. This way, the transformer model knows the exact position of each piece of information in the sequence. Finally, we use a technique called patchify, which is like splitting the image into grids or sections for easier processing. It's similar to how you divide your homework into different parts to work on them separately. This helps the transformer model handle the image information effectively. So by transforming the latent tensors into token sequences, adding positional encodings and using patchify to divide the image information into grids, the diffusion transformer model can efficiently compress the image data during training, and then decompress it back into a clear image during the generation process. It's like translating between different languages so that the magical book can create beautiful pictures from stories and vice versa.
How does the Diffusion Transformer Design Space contribute to the overall functioning of the model in terms of transforming latent tensors into token sequences, applying positional encodings, and utilizing patchify for image processing within the transformer models? Could you explain how these design elements work together harmoniously to enhance the capabilities of the Diffusion Transformer model in image generation tasks?
In the Diffusion Transformer Design Space, where we explore new ways to use transformers for image generation, there are key components that help in transforming latent tensors into token sequences and processing images effectively. Let's break it down. 1. Transforming latent tensors into token sequences. In this design space, the latent tensors, which are compressed versions of images, need to be converted into sequences of tokens that the transformer can work with. To achieve this transformation, a process called patchify is used. Patchify divides the latent tensor into a grid structure, where each grid element is then projected into a token. This projection is done by applying a convolution operation with specific parameters, resulting in a sequence of tokens that represent different parts of the input image. Then 2. Applying positional encodings. Positional encodings are essential for transformers to understand the relative positions of tokens in a sequence, especially since transformers do not inherently understand spatial information. By applying positional encodings to the token sequences derived from latent tensors, the transformer can incorporate positional information into its processing, allowing it to maintain spatial awareness when generating images. 3. Utilizing patchify for image processing. Patchify plays a crucial role in breaking down the latent tensors into smaller patches or tokens, enabling the transformer to process them effectively. By dividing the image into patches and projecting them into tokens, the transformer can focus on localized features within the image and generate more accurate and detailed results. In summary, within the Diffusion Transformer Design Space, the mechanism of transforming latent tensors into token sequences, applying positional encodings, and using patchify for image processing are vital steps that enable the transformer models to understand spatial information, process images efficiently, and generate high-quality outputs.
Can you elaborate on the implications of the Diffusion Transformer model's approach to image generation, specifically in terms of its potential applications and impact on the field of computer vision? How does this innovative integration of diffusion models with transformer architecture pave the way for advancements in generative models and image processing techniques?